So here the question is about which of the 5 cases cannot be in rotational equilibrium. The way we do it to see whether it has both counterclockwise and clockwise rotation enabled. So let me take this one for example. So this is the fulcrum. So the torque from this will be 0. The torque from this will be positive. Torque from this one will be, this will be positive, this will be negative. Okay, right? Because this is the pivot point, this time root negative, this is positive, this will be positive, this will be 0. So you have at least one positive, one negative. So we have the freedom of changing the magnitudes of the forces. So we can adjust the magnitude so that is the positive and the negative will be exactly equal. Then we'll have a 0 net torque. So if you look at this one, same story. We will have, this is, what is this one? Positive. This one is negative. This one is positive. You don't have to continue because we got at least one positive and one negative. So it is out. This one, if you look at this is the fulcrum here. Always pay attention to where the fulcrum is. This is positive. This is 0. This is also 0. This is positive. And this is 0. You know the reason for this 0? Not R is 0, right? But fine. So it is 0 degree. Theta is 0. So there is no parallel component. So you can say sine theta is 0, sine 0 is 0. Or you can also say it is, there is no perpendicular component, only parallel component. So that's the only one that cannot be brought to rotational equilibrium. The rest of them, we have at least one positive and one negative. So we can adjust their sizes to make the net torque equal to 0. Then let's do this question. Here we have a man standing. Standard man means his mass is 70 kilogram. So we are looking at 1 foot, say the right foot or the left foot or whatever the foot. So here, this is what we are looking at. The heel is touching the ground. So you'll have a normal force coming from the ground on him. Let me call it N1. And his toes touching the ground again. So there'll be a normal force from there. Let me call it N2. They will be in general different. And there's one more force. We are looking only on the foot, the right foot or 1 foot. Okay. So above, there will be the everything else. The bone will be pressing down on him. That will be the weight of the man, not entire weight, right? Because you only looking at one of the foot. So half of the weight will be on 1 foot, the other half will be on the other foot. So we'll call that, so it will be acting here from this bone above, it will be pushing on this. So we'll call this as F external, and you know it will be half of the weight of the man. So that's why we get this value. It is given to us. The weight of the man is given, so half of the weight will be that much. So it's like now we simplify the problem to a simple physics problem. So this is the object. We have N1 here and N2 here, and here the W2 over divided by 2 here. Oops, the location, let me match with this. Okay, it will be here. So we are going to apply the rotational equilibrium because he is not moving. There is translational equilibrium as well as rotational equilibrium. We have complete equilibrium. Okay, there's no motion. So let me start with the translational equilibrium. Net force in the y direction is 0. Okay, we can also have net force in the x direction also 0, but it is not going to help us that much. Do you have any horizontal forces? No, it will give you 0 equal to 0. No additional information, no useful information. So we'll go to the y direction. So we can say N1 is positive, good. The external force or the weight, half of the weight is down, negative. and the N2 is also positive, add them and you say it is equal to 0. So we just rearrange that and you get this. So the total weight is equal to N1 plus N2. Total means half of the weight is equal to N1 plus N2. N1 and N2 are the force in one of the foot. Okay, so that's clear. Can I find N1 and N2 with that equation? Oh, so for example, if I say X plus Y is equal to 5, can you find X and Y? How? But I don't know X, I don't know Y. I don't know X, I don't know Y. Oh, okay. You are okay. So this alone we cannot do anything, right? That's my point. Okay. So you are telling the other step. So if you stop here, only one equation and two unknowns. I mean, we cannot do anything with that alone. Okay. So we need to find another independent equation, and we have one. Sigma fx equal to 0, useless. It will give you just 0 equal to 0. So now we know we have another equation, which is the net torque equal to 0. That is for rotational equilibrium. So that is this. Net torque equal to 0. That is rotational equilibrium condition. We haven't applied this yet, so we can apply it now. And when you say torque, if someone say find the torque of this force, is that a complete question? No. You have to tell me, talk about which point. Because you know, depending on where you want to take the torque, the answer will be different. So this equation, net torque equal to 0, is true whatever point you choose. So you can choose, for example, point A. You can choose to apply this about the point A. You can choose to apply about this point B or about this point C or any other point, even it can be outside of the foot. It is true, if it is in equilibrium, you can say the net torque equal to 0 about any point that you choose. Okay, any point. But we have to choose it wisely so that you get the answer to the questions. What is torque? This one? Now you're asking me to do the whole lecture from the beginning. It is too much. Actually, too much. Then I have to spend 1 hour, 2 hours explaining. Because this is the problem. You should have come ready. Yeah. Anyway, I can tell you briefly. If you want, say you have a bar that is pivoted, okay? So you apply a force here, say 10 Newton, and at a distance of 1 meter, and you apply the same force here, say the same 10 Newton, but here the distance is 2 meter. Is there any difference between these two application of the force? You apply the 10 meter, it is like this one is pivoted here. You apply 10 meter here, and you apply the 10 meter here. Is there any difference between that? No? Okay. Right. Let me put it again. Okay. You say this is the door. Okay. This is the door. You want to open the door. This is the door. Okay. So the door can go like that. Say you want to open the door. You pull it from here or you pull it from here. What is better? Farther the better. So for turning rotations, what matters is the torque, not just the force. So we went through all that. Now you are coming in asking me, this is not fair actually. You are, at least should have done your homework before coming to this class. The torque is equal to R. R is the distance from the pivot point, the rotation point, to where the force is applied, multiplied by the perpendicular component of the force. So now let me explain that too. So this is the door. Okay, this is the door. So I asked you, if you pull from like this or from here closer, which is better? You said farther. Let me ask another question. Suppose you pull the door like this to open the door, will it open? So what matters is only the perpendicular component. So the torque is the tendency of the force to rotate, if you put it in another way. So it depends on the R and the perpendicular component. Whatever the parallel component will not contribute to the rotation. Okay, now let me get back. So the net torque equal to 0. So for equilibrium, we need to have two conditions. The net force is equal to 0 as well as net torque is equal to 0. So above the point, any point you can choose. So I'm going to choose A, B, one of these three, or you can any point. It is true for any point. But you need to choose it wisely. Why? Suppose I choose the point B. Let me take a counter example. When I choose the point B, the torque from the force N1, it is not a 0. There will be some torque from force N1 because the R multiplied by N1. There will be a torque from N2 also. Again, in the equation, you will have both N1 and N2. That's not a good strategy. You choose the point such that you have only one unknown. So you can solve for it. So that's why we choose the point A. Well, you can choose the point C as well. When you choose the point A, the torque from N1 will be 0 because force N1 is acting at the point A. What is R? The distance from the pivot point or the rotation point or where you want to take the torque to where the force is applied. It is the same point. Can you draw a line from same point to the same point? Yeah, you can say yes, with the equal 0 length. So R is equal to 0. Therefore, the torque is 0. So that's why if I choose the point A, N1 will not appear in the equation. N2 will appear in the equation. So only one unknown I can find. I can solve that equation and find the N2. So let me continue now. So I'm choosing the point A and we're going to say 0. So how many forces we have? Force N1, find the torque due to N1. Find the torque due to the external force or the half of the weight. Find the torque due to N2 equal to 0. Now this is 0. Okay. Now this one is the external force is this guy, right? Multiply by, this is the point A. This is R. Do I know R? Well, it is given. It is given to us. It's labeled X1. So I will type X1. But you have to wait here because this is only the magnitude. Now you have to decide the direction of the torque. Direction of the torque. The best way to see whether that force going to rotate it clockwise or counterclockwise about the point A. This is the point A, right? And this is your force. Imagine I'm holding it at the point A because that is the fixed point now because I want to take the talk about the point A and imagine this is the only force. Which direction will it rotate? Clockwise. Clockwise is negative. So we put the negative sign. So first get the magnitude of the torque for R multiplied by the perpendicular force. So that is fine. The force is anyway perpendicular, right? And then put the sign because it is clockwise rotation, you put the negative sign. Now you go to this one. So this is this guy, right? What is R? R will be this much from here to there. And it is equal to x1 plus x2. And the force is N2. It is perpendicular already. Do I put a positive sign or negative sign? Look at how it is going to rotate about the point A, counterclockwise. So positive, equal to 0. So we got the equation now. Good. So the equation is this. This is given to us, right? F external is given to us. Now we have calculated it, okay, from whatever the value is given to us. X1 and X2 are given to us. What do we do now? You can do the algebra, but even better, just take the calculator, tell the calculator to do everything for you. Just you type in the equation. So let me show you that. Yeah, sure.
When measuring the torque, we set the point that we want for it to be the fulcrum, right?
Yeah. Yeah. Measuring the R value, you mean? Yeah. From where the fulcrum, where you want to take the torque, it doesn't have to be the fulcrum, the support or the pivot point. You want, it can be any point. From the point where you want to take the torque, you draw a line to where the force is applied. That is R. Right. So all you have to do is to enter here. What is the equation? 0. So you can just type 0. You don't have to do that, but no problem. Minus x1. What is x1? Somebody tell me. I'm covering it here. 6.2. Yeah, it is in centimeter, right? Do I need to convert it into meter? Probably no need, because why? You have an equation, right? In each term in the equation, both left side and right side, the distance is there. So if you convert it into meters, what you're going to do is divide by 100. You're going to divide by 100 on each term. So it doesn't really matter. It will get cancelled, right? So you can keep it in centimeter. That's fine. So let's do it. X1 is 6.2 multiplied by F external is 343, which I have calculated already. 343 plus, what do you have now? X1 plus X2, start a bracket. Says 6, you don't have to do the calculation manually. I mean, one by one, you just write the equation, the whole thing. X2 is 12.3. Close the bracket, multiply N2. Do I know N2? No, that's what we want to find out. What do? We call it X. How do you type X here? Alpha, right parenthesis. Then this is the equal sign, the symbol, right? Not the operation. So how do I get that? Alpha calc. Then what do? Equal to 0. So you wrote the equation in the calculator. You don't have to do any algebra, moving things here and there. You just tell the calculator to give me the answer. How do you do that? Shift calc. So it will calculate the answer. Is this the answer? No. There is one more step, okay? You should see x equal to something, right? So after that, there is another step. What is the another step? Is pressing the equal button, the operation. So let me press that. Right. That is, you should see something like that. This is the equation that you wrote. And the second line is the answer, the solution, x. And the third line, it is verifying the answer. It will put the x back into the equation and see whether the left side and the right side are equal or not. So it should be L minus R must be 0 if the left side is equal to the right side. So that is verifying the answer. So that is the answer. What is it? X. X mean N2. All right. So we found the answer N2. Can you now find N1? Yeah. Go back to the original equation. N1 plus N2 is equal to 343. The subtract. Good. Let's go to the next slide. Yeah.
It would be positive or
no, I depend on the question.
it's counterclockwise or clockwise, right?
Which one will be positive? You mean no, n, when I say n1, n2 are magnitude, right? So if you get a negative answer for n1 or n2, that means you choose the wrong direction for n1 and n2, then you have to flip the direction. But you know n1 is up. So if you get a negative value for n1, that means you made a mistake somewhere. Okay. Right. Now, some physiological application. You heard levers. Let me explain that. Okay. We talked about the lever arm before, right? Yeah. Moment arm. Yes.
Excuse me, because I have a midterm right now.
Midterm?
Yes.
Okay.
I have
I'm not taking attendance anyway.
okay.
So, what midterm you have? Excuse me? What midterm you have? You have a midterm now?
Yes, ma'am.
What is that?
No, it's makeup because I had the midterm. Excuse.
Okay.
Thank you.
Right. Now, lever, I talked about, when you said the torque is equal to RF perpendicular, you can also switch the sine theta with this, then you can say torque equal to R perpendicular F, that is the lever arm. But anyway, here, let me explain the meaning that comes here. Say there's a big rock, okay, and you want to lift it. Let's say it's 100 Newton, the big rock. So you don't have the strength, so you're weak. You cannot lift it. 100 Newton means something like 10 kilogram. Let's say you cannot lift it. What do? You put a rod or bar or something. You put a wedge or a support here. Then this distance from the center of this object to this is maybe 1 meter. Okay, 1 meter. Say this distance is 1 meter from the center of the object to the support. You, although you are not that strong, but you can apply let's say maximum you can do, maybe small child, she can only lift 1 kilogram. So that means about 10 Newton, right? 1 kilogram is about 10 Newton. What is the trick you have to do now? It is lifting mean you are countering, this rock is trying to rotate above the support counterclockwise. You have to give a torque clockwise. At least you give equal amount, you will be able to equal little bit more than equal, say equal, what we will find out how much to make it equal. What is the torque here? 100 into 1 plus 100 Newton meter. So at least we apply 100 negative, you will be able to lift it. So you should apply the force how far away? 10 meters away. If you understand the torque concept here. So you can lift it. This is called the lever. And this lever is called class 1 lever. Class 1 lever is when the support or the fulcrum is another word. The fulcrum is in the middle, it is class 1 lever. So here you see the support is in the middle, and the other two. What are the other two? The load is the weight that you are trying to lift. Okay, that is the load. And where you apply the force, the effort is the other one. So you have three things, right, in a lever: the fulcrum, load, effort. Remember them in the same order. I'll tell you why. Now we can do it right now. There are three things. Remember them in this order: fulcrum, load, effort. Fulcrum, load, effort. Don't change the order. When the fulcrum is in the middle in a lever mechanism like that, we call it class 1 lever. So we have an example of class 1 lever in your body physiology. This is the skull, right? And the skull it is kind of separate from the rest of the body. Okay, not counting the skin and all, skin is continuous. But if you only look at the bone, this is separate from the rest of the body. And it is supported on something like the fulcrum. It's just sitting on, what is it? Spine. vertebrae or whatever you call it. So it is just the skull is sitting on this. So if I draw it again, I hope I can do a good job. So there is a muscle here. Do you know what this muscle? The skull is connected to the spine. Trapezoid, or trapezium. All right, am I right? Yeah, I keep forgetting. It's a trapezium or trapezoid or something. Okay, that muscle is through a tendon or whatever. It is connected to the spine. Okay, and this skull has a certain weight, and the support is here. It is supported on this vertebrae. This is the fulcrum, and weight is on the other side, the center of mass of the skull. Okay, now suppose you are in my class and you are sleepy. All right, this is supported. It's like this. Here you have the muscle which is connected to this. So you have a tension like that. And the load, that is the center of mass, the whole weight is concentrated here, is like this. So your skull doesn't fall forward. Why? The muscle, the trapezium muscle, it's not trapezium, I don't know, I'm getting it wrong, trapezoid or trapezius muscle or whatever, okay? It is, when you are going to fall like this, is not letting me fall because the muscle is pulling you back. But if you are sleepy, the muscle relax. Then you go like that, right? When you are falling asleep, you will fall forward because the muscle has relaxed, the tension is released, no tension in the muscle, then you. Okay. Then, number two, class 2 lever is when I gave the order, right? Fulcrum, load. Load is in the middle. Here it is. When you are in tiptoe, the load is in the middle. The whole weight of your half of the body, let's say if you're looking at only one leg, half of the body weight is in the middle. And here is the support because you're in tiptoe, okay, or tiptoe. This is the normal force here. So that is the fulcrum, okay, this is the fulcrum where it is supported, okay, it is pivoted around that. And if you know, because the weight is going to pull you back, right? It is going to rotate you above this point. Which kind of rotation is clockwise rotation? So you need a force up to stop you from rotating, coming back to the floor, rotating, say, myself. I have to put it like that so to imitate this picture. So if when I'm doing like that, my load is trying to rotate me this way, but it is stopped by another muscle here. What is that muscle? Achilles tendon. The same name? It's connected. Okay, tendon is Achilles tendon. It is connected to the muscle. So we have to look at the tendon. Okay, tendon is the one that is connected to Achilles tendon. Achilles tendon. Yeah. Anyway, fine. So right. Class 2. What should be the class 3? Effort is in the middle. Do you know the example? The forearm. Okay, the forearm. The forearm, the weight of the forearm, even let's make it big, more dramatic, we can put a dumbbell or something. You can have a dumbbell in your hand. So there'll be a lot of weight. We can ignore the weight of the hand. So the dumbbell is maybe 10 kilogram or whatever. So this is, say, 100 Newton. And this is the support. The pivot is the support. So you are trying to lift it, something. So this going to try to rotate it clockwise. So who is going to stop him? Bicep. The bicep is connected somewhere in the middle. So that is what? This is effort, right? So effort is in the, okay, yeah, it is then class 3. Effort is in the middle mean class 3. Support is in one end and the load is in the other end. Whether which end doesn't matter. Okay, it doesn't matter whether it is the left end or the right end, doesn't matter. What you should look at is the who is in the center. So memorize like this: fulcrum, load, effort. Okay, good. Question. The next slide shows 3 bent lever arms with the fulcrum indicated by a dot and a single force F acting at the far end of the lever arm. Which of these 3 systems is in mechanical equilibrium and does not rotate as a result of the force? Right. Let me go one by one. So he's telling which can be in equilibrium, which is in equilibrium. So we need the rotational equilibrium and the translational equilibrium. So let me first go to the rotational equilibrium. This is the fulcrum where it is joined. So R is this, right? Let me use a different color. This is R. And this is F. R is not 0. F is not 0. So is there a torque? What about sine theta? There is no parallel component, right? There is no perpendicular component, only parallel component. Or in other words, you can look at the theta. Theta is equal to? No. 180, yeah. You have to bring tail to tail, right? Sine 180 is also 0. So you can see there's no parallel component. So rotational equilibrium is there. What about the translational equilibrium? It's also there. Net force is 0 because you don't see the other force that is balances. It's in the support. Okay, because it's like, at the support also there are forces that will balance this force. Okay, so translation equilibrium automatically there. So rotational equilibrium is there. So A is in equilibrium. What about B? No. R is not 0, F is not 0, and we have a perpendicular component. Theta is not 0 or 180. So the perpendicular component is this much. Okay, this is the perpendicular component. So R is not 0, F perpendicular is there. There is no rotational equilibrium, so it is not in equilibrium. What about this? Same story. Okay. Next question. Yeah.
Why all of them come down?
Why all of them?
Yeah.
Just, whoever made the question.
No,
The direction of R. Okay. R is a vector. Okay, R is a vector. So definition of R is you start from where you want to take the torque. So he is telling the torque about the fulcrum, the black dot. So you have to start drawing the line from the black dot where you want to take the torque to where the force is applied. So that is how you get the direction, not the other way around. You shouldn't start from where the force is applied. No, you should start from where you want to take the torque and draw the line to where the force is applied. Okay. Okay, this question. Easy question. So somebody is standing on a light board, means this has no mass. So the plank itself has no mass. So there you don't put the weight, okay, because it has no mass. And the plank is supported by 2 ropes, one here and one here. And is kept horizontal, like in the picture. And a man is standing somewhere, not in the middle, somewhere closer to the right side. And he has a weight, 85 kilogram. So that means there's a force because he'll be pressing on the plank, the normal force by him, which is equal to his weight. So the plank is acted upon by 3 forces. So we reduce the problem like that. There's a plank and there's a force here, T right side, tension left side, and the weight of the man. 3 forces are acting on this plank and it is horizontal That means it is in equilibrium, right? It is in equilibrium. Okay. It doesn't say in so many words it is in equilibrium, but you have to understand it is kept horizontal, mean it is in equilibrium. So we can apply the conditions, equilibrium conditions. So let me go to the next slide. Right. Yeah. So you will immediately you will say, okay, let me apply the net force is equal to 0. In the x direction, no use. In the y direction, I can. So TL plus TR minus mg equal to 0. Right? It's correct equation. Okay. But TL is not known. TR is also not given. Mg is given, no problem. I mean, why don't I just use the rotational condition? Just that with that I can find the answer. I don't have to worry about even writing this equation. So I go jump to this and I choose the point A. Why? The question is to find TR. So I can apply it around A, I can apply it around B, about the point C, I can apply it around the middle point, I can apply it around any other point. It is true for any point. Net torque about any point has to be 0 if it is not rotating. Okay. Or with a constant velocity, let's say the static equilibrium. So let's say if it is not rotating, it is in equilibrium, rotational equilibrium. So I can apply this equation about any point, but we have to be clever. Question is find TR. Okay, so if you choose the point B, it will have the same problem. We will have both TR and TL. If I choose the point C, I will have only TL. TR will not be there. I'm not worried about finding TL. I only want to find the TR. So that's why, okay, TR must be coming into the equation. So I should choose A or B. But if I choose B, TL will also come. So the best choice is A. I mean the point A, right? Okay, so this is the net torque from left tension, torque from mg, torque from TR equal to 0. So TL is 0, good. And mg will be 85, 9.8, that is mg. And the R, because R into mg, right? Okay, show me here. What is from where you want to take the torque to where the force is applied. So R will be this for that. Can you see it is given to us? 4.5. So you substitute 4.5, then you decide the sign. Should I put a positive sign or negative sign? So this is the point about which I'm taking the torque, and the force is like that. Tell me which direction it is trying to rotate. Clockwise, so negative. Then you go to this guy, that is this one. Now let me choose another color. So we will, right, TR, the force, and it is perpendicular, so already perpendicular, and distance will be from the point to where the force is applied, this the whole length of the rod, which is equal to 4.5 plus 2.5, which is 7. And that's it. Got the equation. There is only one unknown. Solve for it, and you get the answer 536. You can use the calculator. You don't have to do the algebra. It's not a difficult one. You can do it. I think that is the last slide.